I am very glad to be here. Everyone is talking about AI these days. I'm going to talk about it too. Matt's keynote talked about why, I think it was titled, Why You Will Be Replaced by Someone Who Uses AI. AI is really going to affect software engineering, and looking at some of the other talks, I think more than a third of them were actually focused on AI or had AI as a subject in one way or the other. So I am going to also talk about AI because it's the topic of the day, but I want to take this in a little bit of a different direction. Everybody knows that we are in a time of change. We feel it in the air. And why is that? Because we are in the midst, because generative AI is the first general purpose software tool that we have ever had. We've had other general purpose tools, like a computer is a general purpose tool, electricity is a general purpose tool, but this is the first general purpose software tool that we've ever had. Now, what is a general purpose tool? A general purpose tool doesn't need to apply to every domain. It's not a universal tool, but it is something where the way in which you intend to use it affects the functionality of the tool. For example, you can frequently identify whether something is a general purpose tool by thinking about what would you draw if you were to try and draw this tool. Like electricity, what would you draw? Like an electrical bolt or something? But if you think of all the different ways in which electricity can be used, well, you would draw a motor or a car or a computer or all these other things. Those are applications of the tool as opposed to the tool itself. Now, previous general purpose technologies were, like I said, were things like steam or technology or electricity. And just like today, the development of these tools was accompanied by this sense of possibility and excitement. Back in the early 1900s, people were very excited about electricity. Some new magazines that were created at that time had titles like The Electrical Experimenter or Modern Electrics. Jules Verne, if you're familiar with him, he wrote about the electrical-powered submarine, the Nautilus, in 20,000 Leagues Under the Sea. Of course, there were also people who were afraid of electricity and what it could accomplish. Of course, there was Mary Shelley's Frankenstein's monster, how did he come alive? Well, because he was given a jolt of electricity into this body that was sewed together from corpses. Or if you think about, or if you go back to Rossum's Universal Robots, it was a play written in 1921, I believe, by Karel Čapek. This is the play, by the way, from which we get the term robot. In this play, this is one of the robots from RUR, Rossum's Universal Robots. They create these robots to be workers for everybody, and eventually, well, the robots rebel and they annihilate the human race. Of course, nobody is talking at all about similar things in terms of AI. But in this world, what do we know? We know that things are going to change, but how are they going to change? Well, last year, Scott Aronson and Boaz Barak wrote about 5 possible outcomes that could possibly arise in this world as a result of AI. And they named these 5 worlds AI Fizzle, Futurama, AI Dystopia, Singularia, and Paperclipalypse. And so this is sort of their thinking of how we would get to these various places. But I wanted to quote from them for a little bit how they describe each of these possible futures. So first, AI Fizzle. In this scenario, AI runs out of steam fairly soon. It still has a significant impact on the world, but relative to current expectations, this would be considered a disappointment. Rather than the industrial or computer revolutions, AI might be compared, in this case, to nuclear power. People were initially thrilled about the seemingly limitless potential, but decades later, that potential remains mostly unrealized. With nuclear power, though, many would argue that the potential went unrealized mostly for socio-political rather than technical reasons. So The next one is Futurama. In this scenario, AI unleashes a revolution that's entirely comparable to the industrial or scientific or information revolutions. These systems grow significantly in capability, and they can do many or even almost all of the tasks that humans can at even better, sometimes better than humans, at a small fraction of the cost. But AI systems in this world are still used as tools by humans, except for a few fringe thinkers. Now, no one treats them as sentient. Now, AI easily passes the Turing test. It can prove hard theorems. It can generate entertaining content. But we get used to that, and no one feels inferior to the AI, just like no one feels inferior to your car because your car goes faster than you do, or feels inferior to your computer because your computer computes faster than you can. AI will, of course, like any revolutionary technology in this world, be used for both good and bad, but like the Industrial Revolution, like the Scientific Revolution, by and large, this will be a world in which it does significant good for humanity. Of course, the flip side of this is AI dystopia. The technological assumptions for AI dystopia are very similar to Futurama. This is a place where AI is, as a tool, it's a tremendously powerful tool. It can be used in a lot of different domains. But the difference between Futurama and AI dystopia is how we use it. This is a place where it strengthens surveillance capitalism. It is being it's being used by governments and corporations to cause massive job losses. It entrenches society's inequalities. All these things that you see that possibly could happen just because of the way in which we misuse tools and we misuse things between ourselves. That's AI dystopia. Now, the same world may have aspects of both Futurama and AI dystopia, but we'll treat these as separate for now. The next world, and this is where we start to get a little bit strange. This is where he said, do things continue more or less as we expect them? And the answer is no in this case. But this is where it's good. Here, AI breaks out of the current paradigm, Aronson says, where increasing capabilities require ever-growing resources of data and computation. It no longer needs human data or human-provided hardware or energy to become stronger at an ever-increasing pace. They improve their own intellectual capabilities, they develop new science, and they act as goal-oriented agents in the physical world. They can effectively be thought of as an alien civilization or perhaps as a new species. But fortunately, either by accident or design, these AIs act benevolently to us and lead us to an AI utopia. They solve our material problems, give us unlimited abundance, and presumably virtual reality adventures of our choosing. In this case, in Singularia, it's like we have these genies that will do almost anything that we want, and we all live in this amazing world. Of course, again, the flip side of this is the paperclipalypse. In paperclipalypse, or sometimes AI doom, this is, again, as the AIs become the super intelligent alien race, but they don't need humanity. And in fact, they've developed this, and they're sentient, but they've developed a series of a set of morality that either doesn't care about humans or is actively hostile to humans because they feel perhaps threatened. They feel like just they're unimportant. We don't know exactly why, but the interaction between AI and these Homo sapiens ends about the same way the interaction between Homo sapiens and Neanderthals did, for the Neanderthals. So people sometimes refer to their belief that we are going to run into AI doom as their P-doom, or in other words, their probability of doom. So note that this is different than things like being concerned about bias or types of misuse. This is really about the belief that the world will literally end, or humanity will literally be extinguished in some way because of AI. So I believe, and part of what I want to try and convince you of today is that your P-doom should be very, very small, practically zero. But creating artificial sentience is something that will require us to both rework our entire existing computing infrastructure and fundamentally reorganize the way in which we do artificial intelligence. But I want to step back. Before I talk about why I believe this, I want to give a fair hearing to the other side. There are many very brilliant people who have a very high P-Doom. This is Yoshua Bengio. He's a Turing Award winner. He's considered one of the founders of the deep learning revolution. He very strongly believes that we are in a position where the chance of us being extinguished as a species is very, very high due to AI. So why in the world would he believe this? He's a smart guy, and he really knows the tech. The answer is that they believe in a theory of mind referred to as computational functionalism. The theory of computational functionalism is that our brains are computers, just squishy ones. And anything that happens in our brain is at least simulatable on existing computers. Thus, anything that can be done in a human brain can be done on a computer. And if we just get a big enough computer, then we will have exactly the same capabilities that in the AI as you would have in our brain. He expressed it in this way. I want to read his own words. Oh, wait, don't go there yet. His hypothesis: human-level intelligence is possible because brains are biological machines, he says. There's a general consensus around hypothesis one, that it arises from a consensus that human brains are complex machines. If we could figure out the principles that make our own intelligence possible, and we have many clues about this, we should thus be able to build AI systems with the same level of intelligence as humans, or better. Rejecting this hypothesis will require either supernatural ingredients beyond our intelligence, or rejecting computational functionalism, the hypothesis that our intelligence and even our consciousness can be boiled down to causal relationships and computations that at some level are independent of the hardware substrate, the basic hypothesis behind computer science and the notion of universal Turing machines. So the second key hypothesis that people with a high P-Doom believe refers to something that they call the scaling laws. In strong form, the thesis behind the scaling laws is that intelligence is defined entirely by the number of connections within the system. We've observed that these systems become abruptly smarter as we create more connections, roughly understood as the number of parameters in the system. So when you look at GPT to GPT-2 to GPT-3 to GPT-4, you see it vastly increasing in capability because you went up an order of magnitude in terms of the number of parameters, the number of possible connections between the different nodes in the system. They say there is no reason to believe that this just won't continue. And so this graph is from a person named Leopold Aschenbrenner. He just left OpenAI. And he published this, I think, last week, where his prediction is that by 2027 or 2028, we will have PhD-level AI researchers, AI researchers. And he says, look, we've got, the human brain has roughly 100 billion neurons, 100 trillion synaptic connections, and we observe that we are sentient. So at some point, if we get a system big enough, it will become similarly sentient. Sentience is the byproduct of computational complexity. Now, the worry is that this is going to lead to superintelligence. Now, the inherent advantages, computers have several inherent advantages over us. They can process things faster. They can think about many types of things faster than we can. Some things we can actually think about faster than a computer, but many things, most things, they compute faster. So if you accept these two theses, number one, that the brain is just a computer, and number two, that scale is all you need, then many things follow. So paraphrasing from Aschenbrenner, Relatively near-term systems will be quantitatively superhuman. They'll be able to think orders of magnitude faster than humans. Based simply on input-output speeds, they'll be able to quickly master any domain, write trillions of lines of code, read every research paper in every scientific field ever written, gain billions of human equivalent years of experience with new innovation in a matter of weeks, work 100% of the time with peak energy and focus, and won't be slowed down by that teammate who's lagging, and so on and so on. Here's where the shift happens. This is where we move from extrapolation to prediction. Aschenbrenner suggests that not only will these deeper resources and they'll have deeper resources and faster processing, but he says that they will be able to think qualitatively better than we can. What does this mean? What sort of thoughts would they have? Well, we don't know because we can't think those thoughts. We're not smart enough. But the way he puts it is he says, it'll generate code too complicated for any human to understand, even if the model spent decades trying to explain it. Difficult scientific and technological problems that a human would be stuck on for decades will seem just so obvious to them. We'll be like high schoolers stuck on Newtonian physics while it's off exploring quantum mechanics. He said, of course, if we take this sort of superintelligence and apply it to every domain, well, we'll see an explosion of capability in every domain. It'll be like going through the entire 20th century on fast forward. We'll have gone from flying being thought a mirage to airplanes to a man on the moon and ICBMs in a matter of years. Well, imagine that being contracted into just 1 or 2 years. Which means that if we have superintelligence and it's doing all these things, the worry is that it's going to lead here. Our inability to understand these AGIs and their qualitative difference from us means that we will just not be able to understand them. And the assumption of these AI doomers is that if we're dealing with an alien superintelligence, then perhaps there's a chance that things might go well, but there are many more ways for things to go badly than for it to go well, and we are much more likely to end up in paperclipalypse or AI doom than some sort of AI utopia. Now, here's the question. Do you buy this story? I don't. You notice that the astounding changes that are predicted are premised upon a transition that we don't understand. The essential jump from AIs will be able to think faster than us, to have more context than us, to AIs will be able to think qualitatively better than us. They will have sentience and intelligence that is better than human, is not only not guaranteed, I don't even think that it's possible. So why don't I think that it's possible? Well, to do that, we get to take a detour into one of my favorite subjects, which is computational and complexity theory. You know, normally when I'm talking about AI, I'm talking with my legal hat on, and I'm talking about the legal aspects of it. I'm so glad to be here amongst all my fellow coders, and so I can go into the technical aspects. So let's start with a really basic question. What is computing? Well, back in the 1930s, 4 different people sort of independently came up with explanations of what computing was. There was Kurt Gödel, who described it in terms of recursive functions. There was Alonzo Church, who defined it in terms of the lambda calculus, sort of an early way of describing functions. Emil Post described it in terms of the ability to rewrite series of symbols by a series of rules. And the most influential of the bunch was Alan Turing, who described it in terms of a machine that could read and write on a tape. And of course, the idealized Turing machine would have an infinite amount of time, an infinite amount of tape, and it would read the symbols from the tape, move along the tape to a different position, and write new information to the tape. And scientists have since shown that all of these representations are, in fact, equivalent. Now, the most helpful of these is the Turing machine, and that's because it was described in a way that is physically realizable. In fact, there was also something and today we talk about something being Turing equivalent or Turing complete to communicate that it has the same potential power to compute as a Turing machine. Now, a Turing machine works by mapping a series of symbols to a logical state. I mean, the simplest logical states are, of course, just true and false, which are typically represented by a binary 0 or a binary 1. But, and you can have more complicated meanings that are given to more complicated series of symbols. But importantly, there's no intrinsic meaning to any of these symbols. The interpretation is provided from outside. And that is an essential part of what a Turing machine is. Remember how I said that the Turing machine is able to emulate any other type of machine. The reason why is because it can create a logical framework by which it has a series of symbols that can be interpreted as if it were the other machine. Now, remember this concept of symbol interpretation. We'll come back to it later. So the next big breakthrough in computation was really in the 1970s. This is Edgar Dijkstra. He was the one who really advocated separating out the concept of computation from the concept of an algorithm. The algorithm is the series of steps that you do in general to solve a problem, and the computation is the physical work of actually solving it, moving, shuffling things around, moving electrons, etc. And he said, if we separate these this way, we can actually study these types of algorithms to see how they are used to solve different problems. This separation allowed for essentially the formal definition of complexity theory as a field of computer science. Now, complexity, in computer science terms, is defined by the number of operations, or rather the number of resources, to a certain extent, that are needed to perform a particular algorithm as a function of the size of the input. For anyone who took your CS classes, you probably did a little bit of this analysis when you were talking about big O notation for your functions. I see a lot of people nodding, yes. So in an ideal Turing machine, of course, you have an infinite amount of time, you have an infinite amount of tape, you can solve any problem in theory. Of course, in any physically realizable machine, you have a limited amount of memory, you have a limited amount of time, and so it's important to understand what kinds of problems you can solve in certain physical constraints. Complexity theory is about identifying these theoretical these conceptual limits that cannot be gone beyond. Now, what are shown here are a number of complexity classes. It doesn't show constant time, but the L is logarithmic time. The P stands for polynomial time, which roughly means that it's a multiplicative function of the amount of the input. Non-polynomial time means that NP is non-polynomial. Means that you're going to have an exponential, the time needed to solve the problem is going to be exponential in the size of the input. And of course, you've got polynomial space. You can trade off space and time, exponential time, and then exponential space. And what is shown here is the range of possible problems that can in theory be solved under different constraints, either time or space. Now, the big one, of course, is this P and NP. This is one of the great problems in complexity theory and computer science in general. We don't know whether P is equal to NP, but it's very important. Most cryptography, for example, is built upon the idea that P is not equal to NP. The idea is that there are certain problems that take so long to solve that other people can't solve them. But if you and I each know the answer to this particular problem, we can use that as a token that will allow us to either validate each other or exchange information. Now, I want to make a point about NP problems. This isn't just that we don't know how. The distinction between P and NP is huge. We can estimate a lot of answers to NP problems, but to actually solve an NP problem means that we have no better algorithm than trying every single input and hoping that we find the answer sooner or later. This is why NP problems take thousands or millions or billions of years to solve, is because we have to try everything. And if there's no answer, well, you just go on computing forever. So this brings me to my alternate theorem number 1. The power of a generative AI system is maximum in class P. So this is based on 2 facts. First, there's a theoretical machines. There are some theoretical machines that are not as powerful as Turing machines. One of these is based upon the idea that you don't always have to write. This is called a deterministic finite automaton, or DFA. There's also an NFA, but that's equivalent to a DFA. What distinguishes a DFA from a Turing machine is this ability to write down state. Now, think about how you build an AI system. There are 2 phases. There's the training, and then there's inference. Training, of course, you are writing state because you write down you update the weights, and that's when you learn. But when you have at inference time, you don't necessarily need to write. In fact, there's a startup out there called Grok, G-R-O-Q. How many people know Grok? A couple people. Their claim to fame is that they're about 100 times faster than everybody else at doing inference. And the reason why is because they have mapped the states of an LLM deterministically, and so that they can actually traverse them, they can traverse them much faster. They're not doing it in real time. And so, but the key is, they're actually treating an LLM like a DFA. That means that you can do cutting-edge, real work in AI with just something that is describable as a DFA. Now, let's assume for a moment, though, you did give an LLM some sort of key value store, or you let it write. Well, then it is exactly equivalent to either a double push-down automaton, which is equivalent to a Turing machine, or a classic Turing machine. So, in theory, any AI system that we are currently building is limited in power to a Turing machine. Now, it is true that they frequently have some sort of element of randomness, the temperature, which adds a little bit, and it technically puts it into a bounded probabilistic polynomial. That's BPP. But you can basically think of everything that an LLM can do, it's in P. What's more, what are these AI systems running on? They're running on computers. A computer is a Turing machine, meaning that even if in theory this could go, it was a higher possible power than a Turing machine, it would still be running in emulation on a Turing machine, which means that unless we both change the fundamental architecture of AI and the fundamental architecture of computers as we know them, we are limited in AI to problems that are in P. That's a fundamental limitation. So, that's the first constraint. The next constraint is the idea of non-computable problems. Now, part of the Church-Turing thesis is that it is possible to compute any computable problem on any Turing machine or any equivalent. But there are an entire class of problems that have been formally proven to be non-computable, non-solvable by a Turing machine. The most famous of these, of course, is the halting problem. Will this program actually end or not? But there are entire classes of non-computable problems. There are non-computable numbers that cannot be computed on any Turing machine, but we know that they exist, and we have found them, we have described them, humans have. That's important. So there is some of you may have heard of Kurt Gödel. I mentioned him earlier. He was one of the people who came up with this fundamental idea of computing. He came up with something called his incompleteness theorem. The incompleteness theorem means that any formally described system, which means any computable system, is either incomplete or it is inconsistent, meaning that there are true facts that cannot be expressed in any computable system. This leads me to alternate theorem number 2. Human sentience and cognition is not just computable. This is a direct challenge, by the way, to computational functionalism. Now, I'll support this theorem in 2 ways. The first is an argument from demonstration. This is a gentleman named Roger Penrose. In 1979, he published The Emperor's New Mind, which was a philosophical exploration of the theoretical power of AI. And what he did is he went through and in an incredible range of situations, he documented ways in which humans performed non-computational processes. And as a result, his conclusion was humans are not exclusively computational thinkers. Sure, we can think computationally. That is within the realm of things that we can do. But we can also solve problems in a different way that we cannot describe computationally. Interestingly, he found that this was true, including in very, very discrete contexts, such as the context of math. He said, the conclusion seems to be mathematicians are not using a knowably sound calculation procedure to ascertain mathematical truth. We deduce that mathematical understanding, the means whereby mathematicians arrive at the conclusions with respect to mathematical truth, cannot be reduced to blind calculation. Mathematicians are doing non-computable things. So, what's the implication? The implication is either that we don't understand computation, which would invalidate both the Church-Turing thesis and much of the way we understand computation, or human brains are not simply Turing machines. Another famous way, the second way in which I'll support this is through a famous thought experiment called the Chinese room thought experiment. This was proposed by John Searle in 1981, or in 80. In this, assume that artificial intelligence researchers have created a system that translates, that is able to converse back and forth in Chinese. And a person will feed it Chinese, and it will process this in some way, and it will hand back Chinese responses. And this is a great system. It is fantastic. It passes the Turing test, i.e., the person outside believes that there's a person inside that can understand and speak Chinese and is fully conscious. Now, here's the thought experiment is this. Assume that what's inside this box is not a computer, but it's a human. And you have a book and papers and whatever else you need in order to run this program as a human. From the outside, this human looks the same as the computer. But the human doesn't know any Chinese. Like, I could be in there, you could be in there, you could follow these directions, you could spit out Chinese letters, but you wouldn't know Chinese. And so what he concluded from that is that there is something that is going on that we can't conclude that the person inside is actually intentionally understanding Chinese. This is a simulation of understanding, but it does not have sentience. It does not know. Now, those who are familiar with LLMs might look at this and be like, man, that's pretty much the description of an LLM. Of course, there are responses to this, and the most classical response is what's called the system response, which says, well, the human in there is basically just the CPU. The CPU is not intelligence. What's intelligent is the software. But if you think about that in sort of the LLM context, what you're saying is that the weights are the consciousness. Have you looked at LLM weights? It's a big pile of matrices. That's it. We're saying that this pile of matrices is intelligent. Do you believe that? Do you believe that if we made it 1 trillion items big, that it would become intelligent? Again, I don't. So this leads me to my alternate term number 3. Turing machines are incapable of assigning meaning. Now, you can see this in the Chinese room argument. There's the person outside the box conversing with the system inside the box thinks that there is a person in there who's speaking Chinese, who knows what's going on. But if you think about it, all of the understanding, all of the intelligence is taking place in the brain of the person outside. It is, whoa. I'll keep on talking, and I'm sure it'll come back. All the meaning that is being assigned to this conversation is actually only happening in the mind of the person who is observing. So I lost my. So this means that in order to have any sort of sentience, what you need to have is an observer. Now, let's talk about the assignment of meaning. Does anybody understand this, for example? Does anybody recognize this? What is it? Binary? Anyone knows what it means? How about this one? Or this one? How about this one? So what this is, the top two, or the second, this is ASCII of Hello PyCon Colombia. This is the integer representation of the ASCII. This is Hello PyCon, phonetically spelled Colombia. We say all these mean the same things. But if you think about it, all those are different. They're symbols. We as observers from outside are taking these and we are mapping them to an internal representation of meaning. And we're saying that these things have equivalent meaning. But there is the requirement of an observer to map this. You have this in your, there is a famous, this is a famous picture by René Magritte. Anybody know what the French says? You can yell it out if you know it. This is not a pipe. And he's right. That's not a pipe. A pipe is something that you hold in your hands. This is a picture of a pipe. But what we do is we intersperse the reality of something with the symbols of it, the representation of it, and we manipulate the symbols, and we say that that's what assigns meaning. Now, you've felt this in all your own experience. Can you imagine you've just written a bunch of code, and you're debugging it, and it does something that you don't want, and how do you know? And you're saying, wait, this has a bug, it's doing the wrong thing. Well, what do you mean your computer's doing the wrong thing? It's doing exactly what you told it. Wrong and right are just in your head. Or, as from the relevant XKCD, the little lights on the computer are all wrong this time. I love this because if you think about it, this is what we do. All we're doing is looking at a bunch of little lights, and sometimes they're right, and sometimes they're wrong. What's more is that interpretation is arbitrary. Anyone seen this picture before? Who sees a rabbit? Two people. Who sees a duck? Who sees both? Now, who's correct? Everyone. Everyone is correct. The answer is that there is no correct interpretation here. There is simply the interpretation which you put upon it. The interpretation is arbitrary. It's an imposition of meaning. Significance is that symbols can be complete garbage in some circumstances and can have a perfectly correct meaning in other circumstances. It is all down to the interpretation and which we put them in. So let's imagine for a moment we are able to write a true AI, smarter, that was not expected. We were able to write a true AI, and we were able to put it as smart as you want, and we were able to compile it into consciousness.exe. That was your excitement for the day, by the way. We load it into a computer, and what we interpret as these electrical changes in electrical potential in the silicon is what we are interpreting as the intelligent thing. But a computer is not the only thing that has, like, different potentials, spin, magnetism, etc. What if we took a piece of metal and we measured all the different spins and magnetic potentials and electrons and everything, and we gave upon that an interpretation that allowed us to see consciousness.exe running on this? Does that mean that this piece of metal is intelligent? And what's more, it's not just one copy of consciousness.exe, it's any copy in any language doing the same thing. The interpretation is arbitrary. And by the way, this isn't actually a metal. That's a metalloid. It's actually a picture of a silicon disk ready for patterning. When we say the computer's intelligent, we're saying that the series of electrical impulses that we read on that disk is intelligent. So, in summary, I've presented three arguments as to why I believe the power of AI systems is currently capped. Specifically, the power of a generative AI system is in maximum in class P, and problems of greater complexity are beyond its capability. Number two, human sentience and cognition are not solely based upon computability. It involves non-computable problem solving. Number three, Turing machines are incapable of assigning meaning. Meaning only comes from outside the source of any sentience. So what does this mean for p-doom? Earlier, I asserted that my p-doom was near zero and that yours should be 2. And the reason why I asserted this is that every argument for AI doom essentially assumes sentience. It assumes that as we scale things up, we will create a sentient artificial intelligence, and then we anthropomorphize. We say a sentient thing has wants, it has goals, it has needs, it has a desire for self-preservation. And because we say it is going to have wants, but this is an alien intelligence that's far different than us, we don't know what this wants, we're going to end up going to AI doom. But it is precisely that transition from quantitative scaling to qualitative sentient intelligence that I believe their argument is weakest. There is no clear arrow connecting sufficiently complex computability to sentience. That is just a story. It's a story that many people are telling themselves, but it's a story that I don't believe. If there are I think that what I've described are core technological reasons why the program structures and computer systems that we currently use do not support sentience. And therefore, there's not going to be a chance for goal-directed sentient AI to form. So why is my p-doom not 0? Why do I have that 1 there? Well, 2 reasons. The first is humans are endlessly inventive. It could be that we discover new algorithmic structures, that we figure out new ways to build computers, and all of those allow us to resolve these problems in a way that I've not foreseen. Some philosophers and actually physicists too suggest that consciousness arises from the interaction of us in time, and that's specifically connected to the decay of quantum particles. I think that that's fascinating. Maybe the computer in the future would be able to interact with that in some way. I don't know. Maybe that's one way. The second thing is that, number 2, these are my theories. I don't know. No one knows. I could totally be wrong. The question is, what do you believe? So, what does this mean? Well, one of the big implications of these series is that, first and most importantly, is that I don't think that AI is going to kill us all. It also, by the way, won't save us. Instead, we are headed to one of these places, either Futurama or AI dystopia. The important thing to realize is that the difference between these two outcomes has nothing to do with AI. It has to do with us. It has to do with the ways in which we build systems and the way in which we choose to use those systems as a society. This, by the way, is exciting. I mean, if you consider these arguments in light of what AI has already been able to do, and there's a whole lot of stuff that can be done by things that are of less intelligence than a fully sentient computer. And a fully sentient computer. That's fine. We have an amazing world of productivity in front of us. There are also policy implications. This means that the responsibility for the future is on us. It isn't in some nebulous other, it's in our own decisions. We will be able to use AI as a tool for either good or for bad, and people being people will use it for evil, for bad things. But this is really no different from any other tool that we have. Computers, the internet, anything that we've got is being used for both good and bad. But like other general purpose technologies, this will probably take decades, maybe a century, to fully integrate into our society. This also has implications for AI research. I mean, we should probably still look at things like alignment and safety and interpretability, but it means that we should be focusing on how do those make the AI more effective for the things that we're doing right now? How do we make it so that it's less likely to come out with a bad current outcome? Safety starts to mean safe for this application, not how do we keep this genie from getting out of the bottle. And policy-wise, it means that if we want to have the chance of getting to Futurama, the world where AI is able to generate wealth and we have amazing productivity and all these various things, then we need to avoid a politics and policy-driven AI fizzle. Do you remember I talked for a moment about one of the ideas of AI fizzle was similar to nuclear technology, a technology with great potential that because we were so worried about safety and the potential for things to go bad in the story that we told ourselves, that we have strangled it. If we had to put the same amount of effort into nuclear-based energy creation that we put into petrochemical-related energy generation, then today we would not be in the same place with regard to global warming. Because we were so afraid, we did ourselves a great disservice. We don't want to be in that same situation with AI, where something that could be the greatest tool and could usher in an amazing world is killed because we're afraid. So, this is our opportunity. Get the AI future we choose. Thank you.